Hi, in this video I will be showing you problem number 25 of chapter 13 section 4. A ball is thrown at an angle of 45 degrees to the ground. If the ball lands 90 meters away, what was the initial speed of the ball? So this involves projectile motion of a problem. The initial angle is given, and then the horizontal distance is given. In order to do this, we need to learn the generic formula for the projectile, and the horizontal distance and the vertical distance for a projectile motion of an object. So we'll do that first. A projectile is fired with an angle of elevation alpha and initial velocity v0 vector. The figure is shown here. Assume that air resistance is negligible and the only external force is due to gravity. Find the position function r of t of the projectile. What value of alpha maximizes the range, namely the horizontal distance traveled? So we'll assume that the projectile starts off at the initial point, namely the origin here. We are going to assume that the projectile is, as shown in the figure with the xy axis, that the projectile starts at the origin here. So we'll make that assumption here. And then the key words are external forces due to gravity. Then we are going to find out the position function r of t of the projectile and the value that it maximizes the horizontal distance. Let's assume that the projectile starts at the origin as shown in this figure. So the force is given by mass times acceleration, and then it also states that the only external force is due to gravity. So if we write that m times g times j, because the gravity, acceleration due to gravity is g times negative j. The reason is the gravity is acting downward. Downward means it's negative y-axis. So the unit vector along the negative y-axis can be taken as negative j. So that's why it's negative mgj. So because it says acceleration, external forces due to gravity. And it acts downwards. Then the numerical value of g is 9.8 meters per second square, which is the magnitude of the acceleration vector is 9.8 meters per second square. As ma equal to negative mg, you are looking at this equation here, negative mgj, cancelling out m, we get acceleration a equal to negative gj. That is, a is a function of t, so we will call it equation 1. From here, remember we are going to find out the position function ultimately. That's what the question is. So in order to do the position function from the acceleration, we have got to get the velocity, which is the integral process. And then from the velocity, we have to get the position function, which is the integral of the velocity. So v of t is integral of a of t dt, which is integral of negative integral of this, which will be negative gtj plus c1, a constant of integration that is also a vector, because v of t is a vector. So by integrating this g, which is a constant, we get this g of t. But it's also given that initial velocity at the origin is given to be v0, which is given in the problem. So using that initial condition, we can prove that C1 is nothing but V0. So GTJ plus V0 vector. So that the constant in step 2, constant vector, is initial velocity vector, which is V0. And again we will integrate this in order to get the position function, which is integral of V of t dt, which will be integral of negative gt j plus V0. So if we integrate that, we get negative gt square over 2j plus V0 t plus again another constant of integration. We'll call it C2 vector. Constant of integration cannot be just constant. Here it is a constant vector. So we will use the initial condition. We will assume that the projectile, we assumed that the projectile starts at the origin. So R of 0 equal to 0. So the projectile starts at the origin. So this means that R of 0 equal to 0 vector. So using this and substituting this into the previous step, in step 4, we get R of t equal to negative half g t square j plus tv0 plus 0. So that will be just tv0. But what is v0 vector, the initial velocity? So the initial velocity is making an angle of alpha that's given here. So we are going to write that initial velocity in the component form or the ij form, the horizontal component of that. So if I show a figure here, it's v0 here, then it makes an angle of alpha. So the horizontal component and the vertical component. So this one is going to be V0 cosine alpha, and the vertical component is going to be V0 sine alpha, where V sub 0 is the magnitude of the vector V0. So it's V0 cosine alpha I plus V0 sine alpha j, where V sub 0 is the absolute value of the initial velocity, the length of the vector, initial velocity, and alpha is the angle of the initial velocity, which is given in the problem. So we'll substitute this information into step 5. So this is step 6, and we will substitute the value in 6 in step 5. So which is R of t is negative half gt squared j plus t times V0 can be replaced by V0 cosine alpha I plus V0 sine alpha j. Keep in mind this V0 is the vector. This V0 is the magnitude of the initial velocity. So now we can rearrange I and j terms, which is V0 cosine alpha ti, then V0 sine alpha minus half gt square, V0 sine alpha t. So this is j component, and we'll call it step 7. So we have R of t is given by step number 7. So we can make the horizontal component and the vertical components written in terms of parametric equations. So the parametric equations of this R of t is x equal to V0 cosine alpha t and y equal to V0 sine alpha t minus half gt square. Call it step 8. So the question is also asking in this example, what value of alpha maximizes the horizontal distance? So when the projectile reaches the ground, y coordinate will be 0. then the horizontal distance will be x. So to find what alpha maximizes the horizontal range, we have to use the fact that then when the projectile falls onto the ground, then the y component, y coordinate of r of t will be 0. Y component of position vector r of t would be 0. When the object reaches the ground, y equal to 0 and x equal to d, which is the horizontal range or the horizontal distance. So set y equal to 0 in r of t that we found out earlier. We get v0 sine alpha t minus half of gt square equal to 0. Common factoring the t, we get t times v0 sine alpha minus half gt equal to 0. So one t value is 0. The second t value can be obtained by solving the inner parentheses, the one inside the parentheses. So if we solve for t from here, it's v0 sine alpha times 2 divided by g. So we are going to substitute this t into the x. So 1t corresponds to the initial position of the particle, which is the origin. The second t corresponds to the maximum range of x. So x equal to, from what we have proved earlier, v0 cosine alpha t. So v0 cosine alpha t can be replaced by what we got here. That will be 2v0 sine alpha over g, so which can be written as v0 square 2 sine alpha cosine alpha over g, which is v0 square sine of 2 alpha, double angle formula, over g, because 2 sine alpha cosine alpha equal to sine of 2 alpha from trig. So if x has to be at the maximum distance, sine 2 alpha has to be maximum. The maximum value of sine 2 alpha is 1. So this means sine 2 alpha equal to 1 would mean 2 alpha is 90 degrees pi by 2, or alpha is pi by 4 or 45 degrees. Next, we are going to actually show problem number 25, where we are going to use these results. If alpha equal to 45 degrees, then the ball is thrown at 45 degrees. This is what given in the problem. Then ball lands at 90 miles away, which means x equal to 90 miles. Using this information, x equal to 90, which is equal to v0 squared sine of 2 alpha divided by g, but alpha is 45. So we substitute that 45 degrees here. We are going to have v0 squared sine of 90 divided by g. Sine 90 is 1. So we get 90 equal to v0 squared over g. So v0 squared equal to 90 times g. Taking the square root, also making use of the fact that g is 9.8 meters per second square, we get v0 equal to square root of 90g. And then if we compute this value, you're going to have 30 meters per second. Hope this video helps.